Welcome back everyone. Today I have picked up another problem from Jaan Kalda's handout. This is basically a kinematics problem, or you can call it under the mechanics section because various types of concepts of mechanics are involved in this problem. Right. So let's read out the problem once. A hinge structure consists of two links of length 2L. One of its ends is attached to a wall. The other is moving at a distance 3L from the wall at constant vertical velocity v0. Find the acceleration of the hinge connecting the links when we are given two cases. First case is the link closer to the wall is horizontal. This link is horizontal. And second case is the velocity of the connection point is 0. So let me start with the part A. So in part A, we are supposed to find the acceleration of the hinge point when this left rod or this left link is horizontal. Like this. And so right rod will be something like this, because and this is the vertical line on which this end point is moving with a constant velocity v. This one is constant. This length is 12 and this one is also 12 as given in the question, and this vertical line is at a distance of 3L from the wall. This is also given and it's a constant distance, right? So at this instant we are supposed to find the acceleration of this connection point. Let me name these points. Let's say this one is A, this one B, and this fixed point on the wall is C. So first I will try to find out the velocity of point A at this instant. So let's focus on the rod AC. If we focus on the rod AC, we can clearly see that point C is a fixed point. And as all the rods are rigid, we can apply velocity constant along the rod AC. All the points on the rod AC must have same velocity along the rod, otherwise it won't be rigid rod. So as C is a fixed point, its velocity is always 0. So velocity of point A along C must be 0. Along this direction, velocity of A will be 0. This is my conclusion along AC, right? So whatever be the velocity of point A at this instant, that must be perpendicular to AC. This one, something like this. I'm still not sure about the magnitude of the velocity of point A at this instant, but I have concluded that its velocity will be perpendicular to AC. So let me mark it something like this. This one is, let's say, VA, velocity of point A at this instant, perpendicular to AC. And now we will try to find out the magnitude VA using the rod AB. Again, we'll apply velocity constant on the rod AB. So applying velocity constant on the rod AB, we will conclude that velocity of point A and B along rod AB must be same. So let's equate these two velocities along this rod. So first let me find out this angle. What will be this angle? This length is 2L, so this length must be L as the total distance is 3L given. This one is 2L. So from simple trigonometry, you can easily find that this angle is 30 degree, right? If we assume this one is theta, sin theta will be L upon 2L, that is half. So theta is nothing but 30 degree. And if we extend this line, this angle will also be 30 degree. From geometry you can easily conclude that one, right? So applying velocity constant, we can write that VA cos 30 degree will be equals to V cos 30 degree. So VA comes out as V. So now I am done with the magnitude of VA also. It is nothing but V itself. Okay. But we are supposed to find the acceleration, right? Not the velocity. But velocity is also required for our acceleration. So we'll first try to find out the direction of acceleration of point A. Then we will move on to the magnitude. So let's proceed. Yeah. Now I will analyze the motion of point A from the frame of B. From the frame of B, velocity of A with respect to B will be nothing but 0. What will you do in relative velocity? We just reverse the velocity of the observer and add it with the velocity to the velocity of the object whose relative velocity we are trying to find out. So VA minus velocity of B, that is VA minus of VB, is nothing but VA comma B. That comes out as 0 or be null. Let's write it as null vector. So yeah, if you are in the frame of B, you will observe A is at rest. So in general 2D planar motion, you will have two kinds of acceleration of a particle. You will have a radial component and other one is tangential component. One is perpendicular to the velocity and other is along the velocity. So as in the frame of B, A's velocity is 0, it will have no centripetal acceleration. Centripetal acceleration is v square upon r, where r is the radius of curvature. So if velocity itself is 0, then centripetal acceleration is 0. So I am claiming that A's acceleration, they could have two components of acceleration. This is in the frame of B, right? One is radial one, this one, another is tangential one. So I am claiming that this radial acceleration will be 0, as VAB is 0. But tangential acceleration may have a non-zero value. So its net acceleration is the tangential acceleration. That much I can say. So I can write this AT as A net. And A net means acceleration of A with respect to B. Okay. So let me erase a few terms and write it like this. I was trying to make you understand, that's why writing all those stuffs. Now I'll just write the conclusion. Okay. So yeah, this one is our acceleration of A with respect to B. So we have determined the direction of acceleration of A with respect to B, and now I will claim that acceleration of B is 0 because its velocity is constant, as simple as that. So I have concluded that AAB is equals to AA minus AB, and as AB is 0, this is AA only, right? So this one is the net acceleration of point A. So I have determined the direction of AA and we are trying to find out the magnitude of A, right? So we will need another equation just to relate its magnitude. That we will get again from the reference frame of C. So let's see it on the reference frame of C. So I'm writing here frame of C. From frame of C, as C is a fixed point, we will observe that A is performing a circular motion with velocity v, and this length, as this length is 2L, so we will observe that C is at the center. 2L is the radius of the circular motion and A is performing the circular motion centered at C with velocity v, and radius of curvature or radius of the circular motion is 2L at this instant. And as this velocity is constant, so tangential acceleration will be 0, but we will have a radial acceleration or the centripetal acceleration that will be v square upon 2L. Okay, so we'll use this result, that A's acceleration along C is v square upon 2L. So now it's very simple, I guess, that net acceleration, we know the direction of net acceleration. This one, and its magnitude I have assumed as A of A, and its component along AC is V square upon 2L, and this angle will also come out as 30 degree. So we'll simply write as A cos 30 degree equal to V square upon 2L. Cos 30 degree is root 3 upon 2. So A will come out as V square upon root 3L. Okay, so that's all. This one is the answer for our question. I mean the part A. The acceleration of this link at this instant is V square upon root 3L. And I will not solve the part B, right? You will understand why I am not solving. I am leaving this for you. You just let me know in the comment section what's your idea over this. But interestingly, I can tell you that the answer of part B is also same, but you try to find out why it's same. It's actually, it will be just absolutely the similar problem if you just do one manipulation, and that one is a very simple manipulation. So I'm leaving that for you. I hope you will find out what's the manipulation and you will get the solution very easily. So that's all for today, and thank you.